Hello and welcome to Varsity Eco. I know that I said that there will be a section of types of indifference curve in my last class, but then while delivering the lecture I understood that this is a big topic with 10 different ICs. So I chose to make it a different class, and this is the class. So let's start. To be honest, in my first year of UG also, I was very confused about indifference curves. And then I asked myself how many types there are. And today, in this section, we are going to deal with 10 different types of ICs and their MRS and how to draw them and other stuff. Okay, so we start first with the kind that we actually started, the imperfect substitute. This is the most popular, most used, and almost in all cases we will take imperfect substitute as an example. The classic example is obviously the Cobb-Douglas function, and we will write it as u equal to a into x to the power alpha into y to the power beta. A is positive and alpha and beta lies strictly between 0 and 1. Cobb-Douglas is one of the most famous, important function. It is both homogeneous and homothetic. It has many other different properties. This A does not play a really important role in consumer behavior, but this A has a huge role to play in growth theory, okay, in solo residual. So technically speaking, in future we probably would devote a single class only on this function and its different features. But currently we are interested in the two marginal utilities. So A into alpha into x to the power alpha minus 1 y to the power beta. So this is MUX and MUY A into beta into x to the power alpha into y to the power beta minus 1. Let me also say that sometimes people write alpha and 1 minus alpha. This is a specific case. This is the general version. The reason we have chosen alpha and beta to be less than 1 relates to the quasi-concavity of this function. Okay, so that's again a different topic. So MRS, we can take the ratio A into alpha into x to the power minus 1 y to the power beta. So alpha by beta into y by x. So this is the one property that we should study with respect to MRS, and that property is that MRS does not depend on the absolute values of x and y, but on the ratio y by x. Okay. So now we will move on to the homothetic function. Let me say that our intention here is not to discuss homogeneous and homothetic functions. We are interested here in discussing homothetic preferences and the kind of IC that it generates. You know that for homothetic also we have convex to the origin, but with certain different properties. So first let us write what the preference is. A monotone preference monotone preference relation R on X is homothetic if all ICs are related by proportional expansion along a straight line. Passing through the origin. The biggest application of this we find it in production or cost, actually, the expansion path, right? Okay. So what does it mean? That is, if x are y, then alpha x are alpha y for all alpha greater than or equal to 0. Okay, so what does it mean in terms of diagram? In terms of diagram, this is what it means. Say I have drawn two ICs, and this is U1, this is U2, which is 2 into U1. Now, let us draw proportional expansion along a straight line. So, two straight lines from the origin, right? Through the origin. Say this is point x1 or x, let's say, and this is point y. Okay, and let's say that this point is 2y. What Homothetic Preferences says is that if x and y relates to u1, and if we go to 2u1 and 2y is there, then homotheticity means that this point z will be 2x. It has to be 2x. It cannot be anything else. So that is why the relation R remains intact as long as we multiply x and y, each of them, by the same number. That is homotheticity. That is why this straight line passing through origin factor comes into play. Alongside, I must also say that we know that all homogeneous functions are homothetic functions, but all homothetic functions are not homogeneous functions. So that basically means that the Cobb-Douglas that we have taken, that serves as an example here also. Right? Okay, so now we will move to another typical preference, which is called quasi-linear. The term quasi basically means not quite. So when we are saying quasi-linear, that basically means not quite linear, not fully linear. Okay, so given our two commodities, that means we have two options. So here we can have two different kinds of utility function in general. So one can be this, where x1, first commodity is non-linear and the second one is linear. And we can have a version which looks like just the opposite. So this time x1 is linear and x2 is non-linear. Okay. Now, what is the point of having this? The major point of having this is that these linear components, they can be 0 at optimal. Okay, this is the main advantage of having quasi-linear. And if you have studied further already, or if you are in the final year, then you know that these are the functions that we use for public goods. Okay, they appear in contract theories, they appear in public goods. If you know by this time the Samuelson criterion, then you know that Samuelson used this kind of function where the linear component is the public good. So G2 or G1, whatever you choose. And the other one is basically your other commodities for personal consumption, the private good. Okay, now before we start, let us spend a little time about the behavioral pattern. Because what happens is, unless someone optimizes, it becomes quite difficult to understand. Okay, so in this pattern we are going to discuss a very old problem once given by ISI in its MSQE entrance as a subjective question. So the question was like this. There was a lady called Lakshmi and Lakshmi has two commodities to consume, typically rice and vegetables. Now the behavioral pattern is like this. Lakshmi is poor, so she has little income, and with that money, whenever she goes to the market, she definitely buys rice. But sometimes, if some money remains, only then she goes for vegetable. So there is a situation where she may or may not buy vegetable, but rice is something that she will always buy. So with reference to our functions here, what we are trying to say is that rice is basically the non-linear part and vegetable is essentially the linear part. But more than that, we have two kinds of optimal here, and that we will discuss in detail, taking an example in a separate special class dedicated only to quasi-linear preferences. So two kinds of optimal. One of them is interior solution, by which we mean that both the goods are being bought, and another one is the corner solution, where only non-linear commodity is being bought. Okay, so only non-linear good. And the ICs that we are going to draw later, they are drawn based on this fact that the ICs must be such that they allow, with the budget constraint, this corner solution. Okay. Okay. And also, this whole thing is dependent on income, but in a class on IC, we cannot show that happening. Now we'll go to the definition, and the definition of preference or the description is again taken from masculine. So we will write with respect to commodity 1, the preference relation R on X is quasi-linear with respect to commodity 1, also known as numerical commodity. We will go to that while drawing the diagram. If there are two conditions, number one, all the ICs are parallel displacements of each other along the axis of commodity 1. What does it mean? It means that is x1, x2 indifferent to y1, y2. Then x1 plus alpha, x2 indifferent to y1 plus alpha, y2 for all alpha greater than equal to 0. 0 means basically the same IC, and this alpha factor comes in because we have used this term parallel, so the gap must be same, right? And number 2, good 1 is desirable, that is x1 plus alpha is strictly preferred to x1 for all alpha and x1 strictly greater than 0. Okay. So this second sentence actually tells us a lot of things. For example, why didn't we talk about good 2 is desirable? Because that implies that good 2 can be 0. But if good 1 is also 0, then there is no point of writing all this. So by saying that good 1 is desirable, we are also saying that this numerical commodity is essentially the non-linear one. Okay? Try to understand this. Because if this is not desirable, then we can get in the corner solution the origin only, because x2 may or may not be bought. Okay? Alright. Now we will move on to the diagrams. Now, in drawing the diagram, the basic trick is to understand that if we are drawing this one, then the ICs must be such that x2 can become 0 at optimal. And for this one, just the opposite thing. Okay? Now there is a trick to draw those ICs, and we'll discuss that. We are going to draw them parallelly. So non-linear in x1 and non-linear in x2. Now this implies that x2 can be 0 at optimal, and this implies just the opposite. Now to have these true, here the intersection or the ICs must intersect the x1 axis, and here they must intersect the x2 axis. Okay. Now while drawing them, since here they intersect x1 axis, the original ICs actually looks like this. They are convex to the origin. Okay? Convex to the origin. And the x1 axis, we will draw it here. Okay, so this is basically the difference if you compare Cobb-Douglas and quasi-linear in that sense. Okay. Similarly here, I will draw the x2 axis like this. So this is how it is here. Now, we have kept these two requirements here. So, this diagram here, it clearly states why you use the term parallel, because they are indeed parallel displacements. Alright? Now, let us draw it. Let us take two bundles and understand this concept. So this is our x1 and this is our x2. Say this is a0, this is our y1 and this is our y2. So this is b0. Now let us extend this x2. Let us keep a little bit gap here. Okay. So x2, so this is a1. So that means this point here is our x1 plus alpha. Now, if this is our alpha and if this is added to y1 here, and if our drawing is not that much wrong, okay, so they are not that much parallel. in our diagram anyway. So this will come here, y1 plus alpha. Okay. So that is the basic idea, that because it's a parallel, alpha here works as a measure of parallel displacement, so to say, if you term it. Okay. So we take x1 and y1, shift them by the same amount alpha, and we are going to land on an indifference curve where corresponding to these two we will again get x2 and y2. That is the basic idea of quasi-linear. Now, just as an extra, we will do a little bit math. So take this one which we were working with. ux1 x2 equal to u of x1 plus alpha x2. Now, what is the MRS? MRS is mu1 by mu2 here, which is u dash x1 by alpha. And if you open a book, textbook, you will see most of the time we take this alpha as 1. So if alpha equal to 1, what we have here is MRS equal to mu1. And similarly here, MRS will equal to mu2. And this is the reason that we use the term numerical commodity. Okay. So now let us move on to the perfect substitute. In a separate class, when we will optimize with these preferences, we will understand it much better. So when one commodity can replace another by a constant amount keeping the utility unchanged. Which basically means that MRS is constant. So that means for perfect substitute, our law of diminishing MRS doesn't hold. We'll take a slightly general version, not really typically x1 plus x2. So let's take alpha x1 plus beta x2, and we know that the ICs are simple straight lines, because it's an equation of a straight line if we put u equal to u bar. So MRS mux by mu2, mu1 by mu2, so alpha by beta, a constant number, no law of diminishing MRS. Now, in perfect complements, we call it in many names. We call it L-shaped, which is not really correct, because there can be perfect complements which are not at all L-shaped. Similar, but not really L all the time. And then Leontief function. We call Leontief because if you go through in future, or if you have gone already through the Leontief's input-output model, then you know that the perfect complements or perfect complement preferences, so to say, appeared there first, okay, in that model. Alright, so when goods are desired in a fixed ratio such that consuming beyond the ratio, adds nothing to utility is called Leontief preferences. perfect complements. Perfect complements is referred to the commodities. The preferences is perfectly complement preferences, like that. Now, usually in your class you would have seen the standard scenario, U equal to minimum of L comma K, and the IC looks like L shaped. We've got a straight line going passing through origin with a length of 45 degree, right? And then these are our utility ICs, right? Different utility levels, U1, U2, U3, so on and so on. Now, this has a serious gap in learning. The gap is this. First of all, drawing this is very easy. So what happens, I've seen in the last many years, that you get this one, but if I provide you with something different, right? Something which looks like, say, this one, or if I tell you to draw a Leontief with a functional structure like this one, then most of the students are at a loss. And the more dangerous scenario is that even under these two, somebody will draw an L-shaped utility function looking like this, which is not true at all. But the point is that looking at only this, learning only this, will never make you learn how to draw these things. So we are going to first draw this one. Okay, now the easiest starting point is to understand the optimal. So whatever happens at optimal, you consume at the fixed ratio. Alright. So we'll start at that. So at optimal, x1 star plus x2 star for the first one is equal to 2x2 star, which leads to x1 star equal to x2 star. Remember, this is the same thing that is true for minimum of LK or x1, x2, whatever. Generally, right? So LK is the common example. So anyway, x1, x2. Okay. So what we understand is that the equilibrium points will lie on a 45-degree line. Of that there is no doubt. So this line corresponds to x1 equal to x2. Okay. Now let us choose a specific point like this. So if this is the, let us draw it here. So let's say this is our x1 star, this is our x2 star. Okay. Then on one side, x1 star plus x2 star is equal to 2x2 star equal to our u star. So if I am drawing an IC including this point, let us say this is A, then the utility will be this value, right? Because at optimal they are same. Okay. Now, this implies that x1 star is u star by 2 and x2 star is also u star by 2. So this is going to help us. Now, if x1 increases, that is in this direction if we go, then what will happen? This implies that x1 plus x2 will be higher than 2x2. And if that is the case, then the utility that will be there will be 2x2 star, because that is the lower side. Okay? And that means that x2 star will be u star by 2. So this is our x star equal to u star by 2, so a straight line looking like this. Now what happens in the opposite direction? So if x2 increases, then 2x2 will be greater than x1 plus x2, and this will become your utility. So that means on this side the utility will follow this line x1 plus x2. And how will that look? It will be a line like this with a slope of -1. So now you have got one typical IC and all the other ICs will be parallel to it. So you can simply draw like this. Okay. So never get this idea that because it is perfect complement, it is always going to look like L. Okay, it will have a kink always. Yes, it will be consumed on a fixed ratio following this line, but it is not necessary at all that it will look like an L. Okay, so try the second one at home. Let me know in the comment box if you have succeeded or not. Alright, we'll now move on to the next scenario. So now, neutral preferences. Neutral means you don't feel about any one of the goods. So when the presence of one of the commodities does not change the utility level at all. It doesn't matter. So first we have to select which good is that. So that means if it is x1, that means I can keep on increasing x1 and your utility will not change. So that means to keep you on the same IC, I should do it. Okay. So keep on increasing x1, utility doesn't change. So that means obviously your utility will depend entirely on x2. Okay. And it will increase in this direction. The opposite scenario is this. So your utility will increase in this direction. Here we will write x1 is neutral. Here x2 is neutral. And u1, u2, u3. Oh, you can understand, it's very simple. Okay, so in the next we will move on to concave. Okay, so that means you like them, but you don't like them together that much. Concave preferences. So extremes are preferred than the average. So when each commodity is preferred in isolation but not in combination, that is, extremes are strictly preferred than averages. By the name, it will look like a concave function. Okay. like this. The easiest example is, if we relate to this diagram, a circle with center at its origin and only first quadrant is being considered. So now we will move on to Bliss Point. Theoretically, Bliss Point actually involves a lot of other possible ICs, alright? But the point of discussing it is that Bliss Point refers to the fact that there may be a limit beyond which you don't like anything to consume, okay? And that limit is the Bliss Point. It was famously used by Ramsey in his model, okay? But that is in macro. Preferences can be such that beyond a certain amount each of the commodities become undesirable. Hence, a bundle can be defined. Representing the maximum value of utility that can be achieved. That is a point which lies just in the center of this desirability and undesirability. So this point is called Bliss Point. You need no more than. Okay, that's the idea of bliss actually. Okay, so how to draw it? First we have to decide which one is the bliss point to draw this one. So say this one is our bliss point, some B, x1 star, x2 star. So below these two levels, things are desirable, and assuming that they are imperfect substitutes, convex to the origin. Beyond this point, x1 becomes undesirable. So the IC goes upward. Okay? And why does this happen? Because now it is undesirable. So let us try to understand, right? So now if I increase x1, the utility of that person is actually decreasing. So if I take some x1 here, okay, the utility of that person decreased. So to increase the utility, because we want to return at the same level, I must increase x2 because x2 is still desirable. So I go in this direction, utility decreases. Then to balance it, I go in this direction to achieve the same utility. Alright? So that is how the IC at this part looks like this, which is convex upward. Alright. So the same scenario is seen here also. Okay. Now in this region, both these are undesirable. Alright. So say at this point, if I increase x2, then my utility has actually reduced. So to increase the utility, I must reduce x1 also, because x1 is also undesirable. Okay, so two undesirables. If you increase one of them, you have to decrease one of them. Following that, the IC will go like this. Okay, so this is one way of drawing IC from the English knowledge of preference. So you don't know the function, but you know the behavioral pattern or the preference in English words. Alright, there is a fantastic exercise in Snyder based on this idea that you can actually draw ICs looking at or reading some of the advertisements. Okay, so we are doing the same job. Alright, just to make it look a little more beautiful, I hope. Yes. Alright, so this is how it works and this is how it looks. Okay, now we will move on to the typical one, which is lexicographic. Lexicographic preferences are best understood by the term dictionary preferences. That means if I will give two words, two English words or any word of any language to you, then how will you order them in the dictionary? We will go for the first letter, look at their ordering in your language, then we will choose one of them. If they are same, then you will go to the second letter and do the same job. If they are same, go to the third letter and so on. Lexicographic preferences is exactly like that. Writing it in English words is actually quite difficult. So we will write it in the format it should be written. Okay. So x1, x2 lexicographically preferred to y1, y2. This is lexicographically preferred to y1, y2 if and only if either x1 is strictly greater than x2, okay, or x1 equal to x2 and y1 greater than y2. So this is the thing. You go for the first one, then you, if they are equal, only then you go for the second one. Remember that this is not the only structure. What I am trying to say by this is that here we have made a choice that the consumer will first look for the good one. There can be a lexicographic preference where the consumer will first go for commodity 2 and compare, and then go to good one and compare. Okay, so that is also lexicographic. So let me just write it down for help. So we can have something like this also. If and only if either y1 greater than y2 or y1 equal to y2 and x1 greater than x2. So this is our discontinuous one, and we will show why that happens. So, okay, let us write good one, good two. Right? Let's take a bundle and say this is my x1 and this is my x2, and let's say this is A. Now, to find a bundle which is indifferent to this one. Alright, so these two are gone. If we go any to the right, then x1 will be higher, so it will be strictly preferred. If we go towards the left, then x1 will be lesser. Similarly, following the same logic, what we are left with is this line. Now in this line, if we go downwards, x1 will be same, but x2 will be lower, or good 2 will be lower. So less preferred. If we go up, then good 2 will be higher, so that is strictly preferred. So to repeat it again, on the right side we have strictly more preferred, on the left side less preferred. Go down, less preferred. Go up, more preferred. So that means this point is either point A is either strictly more preferred or less preferred to every other point in this diagram. That means we cannot go beyond this point at all. So that is why the discontinuous preference, the lexicographic preference, where we do not have an IC, we just have a point. Okay? The undesirables, like you are traveling in a bus, you like the bus travel, but you don't like the pollution. Alright? Or both bad. So you have to do homework or assignment, you don't like that, and well, you have to follow some other kind of discipline, which you don't like that either. Okay. Anyways, so there can be two cases. Case one is only one commodity is undesirable. Now we are not going to discuss it very much because we have already done Bliss Point, so we know how it looks like, right? So it can look like this, or actually depending on MRS it can also look like this one, also look like this. Okay, so the undesirables, and coming from Bliss Point, we know that alternatively we can choose good 1 to be good or good 2 to be good, right? And the other case, case 2, is when both commodities are bad. Now when both commodities are bad, that leads to a very interesting scenario. Both commodities are bad. The scenario goes like this. Either I can have convex to the origin and the map looking at this direction, we have seen this, or we can have scenarios of Bliss Point like this, right? And then also the movement is towards the origin. In this case, however, the movement goes to the desirable commodities direction. So let's say if this is your bus travel and this is your pollution, then your utility will increase in this direction, and if you interchange the name of the axis of bus and pollution, then your utility will increase in the other direction. Okay, so these are the 10 types of IC that you will be handling in future. And remember that Lagrangian does not work in all of these cases. Actually, in most of the cases, you will need different methods of solution. Okay, so now I'll make a chart on these ICs and their corresponding MRS just to give you a composite picture. Although we have dealt with 10 different types, in this chart you can see not all of them. So utility functions, that is the names first, Cobb-Douglas, quasi-linear, substitute, complement, neutral, concave, and this one is only one commodity, that is the second commodity becoming undesirable. Okay, because as you understand, if commodity 1 is undesirable, then it will be analogous. Then the structure of utility function, these are taken to some extent general, and in case of concave I have chosen a more slightly specific to make it simpler. Then the mu1 and mu2, obviously because it is complement, so mu1 and mu2 both are 0, because if you increase the utility of one commodity single-handedly, then it will not affect the total utility at all. Here also for the neutral commodity it applies. Okay, so it is written in the same pattern, beta x1, alpha x2, beta or 0. Alright, like that. In those two we have written undefined. We have written undefined. For complements it is undefined only if you think of differentiation, because a kink point is non-differentiable. But if we go by the preferences, which is the actual, then it is actually 0 because it is complement. So there is no idea of substitution at all. In neutral, obviously you have vertical lines and you have horizontal lines. So going by simple geometry or tangent ideas, tan values, it will be either undefined or it will be 0. The rest of it as it should be. last important thing that you should notice that here, because I have an mu which is in negative, the MRS becomes negative. This is typical if one commodity is undesirable, that makes the whole thing going convex upward or concave downward or a straight line, whatever it is, increasing. Okay, but for both commodities undesirable, you can understand that these two MUs will be negative, so end result will be positive again. Okay, so here we finish. In future, when we talk about optimization, we will look at most of these functions which are slightly difficult, has different methods, and we'll look also at the resulting demand curves.